Welcome back to my channel. Part 2 Strut and Tie method, visual movement method, detail calculation. And the first one we has to know about node in STM method, Strut and Tie method. It is a compression node, and it is compression tension node, and the last figure is CTT, compression tension node. And you will know when we call it CCC and when we call it CCT or CTT. If you look at this pie cap, this pie cap supported by two ball pie and apply one column above the pie cap. You see, this is the apply load, and this node it also has two reaction. It's called PU or P, ultimate load, divided by 2. So in this node develop pure compression develop in this node zone. So it's called compression. In one node has 3 compression, and for this node we also apply compression stress here, compression reaction here, and in this one direction we develop tension zone. But don't confuse about the direction here. It's not mean the direction and the direction mean compression. No, I want to explain you in one node, in this one node. So we have compression and tension, but actually in the deep bottom area it's the tension zone. You see the schematic here. So in this node it's called CCT. You hear at the bottom we need more reinforcement to transfer to resist load from this point to this point, and this zone is called C or S, compression zone, and this zone is called tension zone. Why we have to classify about node CCC, CCT or CTT? Because we had to choose the design compressive strength according to each node. If pure compression, we can fully apply 1.0 Neufrim SCD or the design strength of concrete. But in this node contain tension, so we receive 55% of the Neufrim SCD, and it contains 2 tension, so we had to receive more. So we apply 0.75 multiply Neufrim SCD. This is important, so we will not apply the same compressive strength of the concrete in it node. It depends on the fixed type of the node zone. So it is the model as we discuss about apply load. Here apply load, in this zone overlap between the compression and decompression pneumatic strut. It's called nodal zone, and and it developed the battle shape strut like this one, okay, like this one. But we have to idealize primitive strut. It is idealized primitive strut too easy to calculate. We have a real shape, so it's easy to calculate stress and verify stress in this section, okay, in this section, because we can calculate the width of the strut, so we can apply it to verify the stress here. And at the bottom develop the tie, okay, the tie zone. We want to check compression stress, okay, we want to check the compression stress and at this zone. So we had to know about the width of this strut. We call it A2, and the bottom tie dip develop at the tension zone. We can calculate it based on 0.12 multiply minimum L, okay, L distance from one support to other support in the case, and H height of the section, the minimum. But in zero code not has specific value, but according to model code 90 recommendation for the ACI 318 state that the value of the bottom tie dip is should between the 0.5 UT maximum and the UT maximum, where the UT maximum is equal to force multiplied to T divided T multiplied with sigma or D. Note that is the sigma or D note is equal to law of ball designs bearing stress at the bottom node. And the effect of rebar distribution on the zone dimension is you use the one layer of rebar and the nodal zone developed at the bottom of the pie cap or about the support. It look like this one, but as you increase more rebar layer, so the nodal zone will be changed to this one, okay, you see. And from here to here is the LBD width of support, okay, width of support or length of bearing. If you have the pie cap diameter D is equal 80 centimeter, so LB is equal to 80 centimeter. You see here, for the one layer of the reinforcement, the A1 nodal zone is mostly the same with the length of the bearing, but when you increase when you add more rebar layer, the width of A1 so decrease. And here we can calculate the value of A2 according to the formula. All parameters we has been known. A1 sin alpha, U calculate from here, and LB is the length of the bearing we known, and S0 is the distance from the first rebar layer to the bottom of the pie cap. You see here, S0. Now apply to analysis in finite element finite element software. In this software, we have to apply the pie cap as cell element, and we make it 2020, and this column 50-50 receive the ultimate load 600 tons, and we have two ball pie diameter 800, and distance from here to here is 3 diameter of ball pie is equal to 2.4 meter. And for this model, we apply only the same but different the dip of the pie cap. Here the pie cap is equal 1.5 meter, and for this pie cap only 1 meter. So you have to understand about the local axis of the program consideration in this one direction, and this two direction, and this three direction. Which this design convention is not the same with the global direction of the software, but we focus only on with the element. So you see here the maximum did load, maximum did load S11 is mean the no more thread in one direction. So you could see the tensile thread develop in the bottom of the pie cap. Here is more larger than this one. The load applied about is the same, the column about is the same, the distance from here to here is the same, and the ball pie diameter is the same, but what is the different is the dip of the pie cap is different. So the effect developed in the pie cap also different. You see here the dip of the tension zone is increased. You remember the value of u. The value of u is equal to 0.12 of the dip of the pie cap. So it depends on the dip of the pie cap and the applied load with the distance the distance from one pie to the one pie. So for this model, the tension zone developed at the bottom of the pie cap is less than this the model. It is the stress S22, the most stress developed in vertical direction. You see here this value, the minor value in the tab is the compression. So when we apply load in this area, so the compression stress develop here, the compression stress, also the compression stress, the compression stress. This compression stress continue from here to here to here, and this one is called develop from here to here to here. But in the bottom still remain the tension stress developed in this direction. tension stress, tension stress, tension stress, tension stress. In this one is the shear stress in one two direction, shear stress in the vertical direction. So you can see different effect. Just we we apply the different dip of the pie cap, but the other information we keep it the same.